Welcome everyone for today's lecture on module 3 of digital switching system. So far till the previous class we had the discussion of uh, uh, the mathematical model of telecommunication traffic, how it can be used. We have even seen small example problem where we can solve. We have seen where how we can solve the telecommunication related problem. The next two most important topics are the first Erlang distribution and the second Erlang distribution. And these two derivations are asked often in the examination. And basically in this derivation we'll be deriving the grade of service of two of the system that is used in telecommunication. Okay, those systems are the switching system and then the message switching system. Okay, in these two derivations, which is the first Erlang distribution and the second Erlang distribution that we are going to discuss, we'll be deriving the equation for the grade of service of these two switching systems. Okay, first we'll see the first Erlang distribution. Okay, as it says, Erlang determine the grade of service, that is the loss probability of a lost call system having n trunks when offered a traffic. Imagine a switching system where you have some n number of inlets and n number of outlets, and which has no storing capacity or queuing capacity like a message queuing system. This is a lost call system. This is also called as the lost call system. It's because whenever a congestion is encountered in such a switch, okay, the call which is coming after the congestion will be lost. That's why this kind of system are referred as the lost call system. And the derivation that we are going to discuss is depend on the following assumptions: the pure chance traffic, statistical equilibrium, and then the availability. And statistical equilibrium as well as the availability that we have seen pure chart traffic, that we have I guess we have already seen that one in the mathematical model. Okay, the only additional assumption that we are seeing here is that the calls encountered during congestion are lost. As I told you, this is a system which is a circuit switching system. Okay, whenever a call encounters a congestion, it will be lost. Okay, moving on. Okay, what does this assumption say? There are four assumptions. The first assumption says the pure chance traffic implies that call arrival and call termination are independent random events. Okay, and the second assumption, which is statistical equilibrium, which implies that probabilities do not change, okay, even when call enter the system or call leaving the system doesn't affect the probability. This is called as the statistical equilibrium. And full availability means that every call that arrives can be connected to any outgoing trunks which is free. That means as long as the outlets of a switch is free and it's available, any incoming call can be connected to any outgoing call to provide a path between two, okay, partners in communication. If the incoming calls are connected to the outgoing trunks by switches, switches must have sufficient outlets to provide the access to every outgoing trunks. As I told you, in the last call system you have a n number of outlets and n number of inlets. As long as this n number of inlets have calls coming into the system, okay, full availability says that all of them should be able to connect it to the any of the available freely available outlet. Well, the lost call assumption implies that any attempted calls which encounter congestion are immediately cleared from the system. That means any call which is exceeding the number of inlets, or in this case number of outlets, okay, if it encounter the congestion, say for example if call is coming into the switch, okay, and it needs to find a path, okay, it needs to find a path which should be uh, what I can say, we should be connected to some of the outgoing outlet. So say you should, if it is encountering some congestion, it will be lost. You know the nature of circuit switching. Only when the physical connection is available, the connection can be made. If that physical connection is already occupied and it is taken, you no longer support the connection. So moving on, you already know from the mathematical model the probability with which call occur in a system is given by this equation, which is capital A or to the power of x over x factorial times p of 0, where p of 0 represent the probability with which zero call occurs, and multiplied with the factor capital A represents the traffic, x represents the number of calls, that we already seen from the equation 1.7. Okay, as we know, the number of calls coming into the system cannot be negative. That means the number of calls always start from 0. You can have 0 number of calls or n number of calls. That why the interval for the summation of p of x in this derivation is taken from 0 to capital N. N represents the maximum number of outlets or maximum number of calls that can be supported by the circuit switching system, or in this case the lost call system. That's why in order to take summation of p of x over the, instead of taking taking the interval over 0 to infinity, we are taking the interval between 0 to n, because the system can only support some discrete number of calls. That's why the summation of p of x over the interval 0 to capital N becomes 1. Okay, you know the probabilities, sum of probabilities over some interval is always is equal to 1, and substituting p of x in this equation, you'll get the summation of a power x over x factorial times p of 0 over the interval 0 to capital N. Moving on, if you solve for p of 0, you'll get 1 over summation of the term a power x over x factorial over the interval 0 to capital N. Using this we have solved for p of 0. We plug in the same value of p of 0 into p of x, which is 1.7, and we end up in this equation, where it says p of x is equal to a power x over x factorial, the whole term divided by the summation of the term a power k over k factorial, where the summation interval is from 0 to n. Note that the notation for the variable has been changed. In p of 0 definition we have used x, whereas in order not to confuse the x using twice, in this case the x represent in 1.8, the x represent the number of calls for which you want to find the probability, and you don't want to confuse that one with the the interval. That's why the notation has been changed. This equation 1.8 is referred as the first Erlang distribution or Erlang's last call formula. This is an equation that we are deriving, which is called as the first Erlang's distribution or last call formula. Moving on. The p of x you already know. Even in the mathematical model, the probability with which we want to find a particular call occurs was represented with the same notation p of x. In order to not to confuse with the actual mathematical model, a new notation has been given to define the grade of service of a lost call system, or the first Erlang distribution. As you can see, this formula that we have defined in equation 1.8, it is the equation for the grade of service of the lost call system. Moving on, in order to not to confuse the p of x, we are not using the same notation in the equation 1.9. Please observe. We are using capital E suffix 1 comma n of a, which is the symbol or a notation used to represent the grade of service of the first Erlang distribution, and we are going to replace the x with, and as you can see we have x over here in 1.8, and we are replacing x with capital N, which results in an equation, capital A to the power of n over n factorial, whole term divided by the summation of a power k over k factorial in the interval 0 to capital N. Moving on, we can further simplify the same equation, okay, in terms of only a and n, only a and n. In this aspect, we're going to replace the denominator on the right hand side with a definition which only involve a and n. A, where a stands for the traffic offered by the system, where n represent the number of outlets available in the system. Okay, as you know, to replace this, the term in the denominator of equation 1.9, we move on. And moving on further, uh, uh, we replace in the same equation of 1.8, we are going to replace n by n minus 1, which results in the same equation where which has some modification in n, where n is being replaced by n minus 1. Please look, in equation 1.9 you have n, okay, and that's being replaced by n minus 1. Okay, why we are doing this, you'll see as and when we proceed with the derivation. Okay, then moving on down the derivation. Okay, the denominator part has been moved to the left hand side, and the notation for the grade of service has been taken as a denominator on the right hand side. Okay, as you can see the term or the summation a power k over k factorial, the summation of this over the interval 0 to n minus 1 has been split into two terms, which is equivalent of the same. As you can see here, in this case, which the equation in this equation, okay, the equation on the left hand side, which says the summation of a power k over k factorial between the interval 0 to n minus a power n over n factorial, which is as good as summing of a power k or k factorial between the interval 0 to n minus 1. As you can see, we have taken the denominator to the left hand side, and we are representing the equivalent of the same summation in the other way, okay, by subtracting a power n over n factorial from the summation of a power k over k factorial in the interval 0 to n, which is as good as summing of a power k over k factorial, okay, summing of a power k over k factorial between the interval 0 to n minus 1. It's very simple. We are taking the whole interval, the sum of this term over the interval 0 to n, and we are subtracting nth term. And which results in the same summation. Okay, moving down the line, okay, we're going to rearrange the equation, which results in the definition for the summation of a power k or k factorial, okay, between the interval 0 to n, okay, in terms of only n and a, and also the grade of service of n minus 1 terms. Here, as you can see, e1 comma n is in the denominator of the first term, which represent the grade of service of the n minus 1 trunk. Okay, the whole equation is like a power n minus 1 divided by n minus 1 factorial, the whole term divided by e1 comma n minus 1, which is nothing but the grade of service of n minus 1 trunk plus a power n over n factorial. Okay, this definition of the summation is taken and it will be substituted in the equation 1.9. Okay, if you take the definition that we have derived recently for the term a power k over k factorial between the interval 0 to capital N, we take the same term, and if you plug into the from this definition, you take this definition and plug into the equation 1.9, and solving or simplification of one or two steps will result in this equation. Please make sure that you practice the simplification, which I am going to leave it as an exercise to you. Okay, if you simplify by plugging the value of this summation to the equation 1.9, okay, with a couple steps of simplification, you end up with this equation, which is the alternative definition for the L-Long's distribution. Alternative definition for the L-Long's distribution, which says e power n comma n, or B. The term B is used for the representation of the grade of service of a system. E1 comma n of A is equal to A times E1 comma n minus 1 of A whole product divided by capital N plus A times E1 comma n minus 1 of A. This is called as the iterative uh, uh, form of representing the Erlang's distribution. Iterative, okay, form of representing the Erlang distribution. We'll be seeing as example problem how this equation can be used to solve the telecommunication related issues. Okay, and also note that the Erlang for zero, the first Erlang distribution for zero trunks is 1. Okay, the first Erlang distribution for zero number of trunks, okay, is 1. Okay, I hope you have understood the meaning of this equation. Okay, moving on, we'll see an example problem, okay, which says a group of 5 trunks is offered 2 elongs of traffic, and you have been asked to find the grade of service, okay, the probability that only one trunk is busy, the probability that only one trunk is free, and probability that at least one trunk is free. Okay, so to find the grade of service, you know the number of trunks and the traffics available. So you directly using the equation 1.8 that we have defined in the first Erlang distribution. They are taking the equation 1.8 that we have recently discussed, and they are plugging in the same equation by expanding. As you can see, you know the value of A. A is nothing but the traffic of a system, traffic offered by the system, which is 2 Erlang. Capital N is 5. Okay, N represents the number of trunks in the system or outlets in the system. 2 is the number of, 2 represents 2 Erlang represent the traffic that is encountered by the system. What is 2 power 5, which is 32? What is 5 factorial, which is 128? This whole term is divided by, okay, the sum of the term a power k over k factorial between the interval 0 to k is equal to 0 to n. You know n is 5. Okay, you only get, okay, from 0 to 5 you get the 6th term. Okay, 6th term, and you need to, okay, expand it and find the sum of it in the denominator of the equation, okay, to find the answer. Okay, you know a power k is a power 5, sorry, k, when k is 0, a power 0 becomes 1, k factor 0 factorial becomes 1. That's why the first term is 1. Okay, similarly moving on, a is 2, k is 1. Okay, the k factor k, as k is 1, 1 factorial results in 1, it is 2 over 1. Okay, similarly moving on, you plug in the values of k and you keep on expanding this, and you result in a sum of 7.226 in the denominator and 0.226 for the numerator. Please practice this. Okay, if any changes in the calculation, please verify for the value of this calculation by doing the practice. Okay, so 0.2267 or 7.2667. Okay, by dividing this, you will get the grade of service of the lost call system if you have a 2 Erlang of traffic and 5 trunks are available. This is 0.037. Similarly, in order to find the probability with which only one trunk is busy, okay, you need to find the grade of service of that, okay, number of trunks. Okay, instead of 5, okay, you're going to replace n with 1, okay, which results in a equation 0.275. Okay, you know the definition. K is the like x is the number of calls, or in this case n or x. You can use the term interchangeably based on the equation definition that you're using. Okay, so in this case, the n is 1. We are plugging in the value 1 to n, and a remains the same, and expand the same equation results in a okay, same some value which is 2 or 0.275, which is the grade of service if okay, only one trunk is busy. Okay, then moving on, we are trying to find the probability with which only one trunk is free. That means it is the indirect way of asking what's the probability with which 4 calls can occur, or what's the grade of service if 4 trunks are occupied in the system. Okay, this is the indirect way. What is asking the probability that only one trunk is free? It is as good as asking you what's the probability that 4 trunks are busy. So that's why we are taking P of 4. Okay, by substituting 4 into n. Okay, we results in a it results in a value 0.01 0.0917, and is asking, the last question is, what's the probability that at least one trunk is free? Okay, in this case is asking what's the probability with which only one trunk is, okay, free, and you know, and other one trunk is free is asking. This is the alternative question for how, like, what is the remaining probability of at least one call can pass through the system if all 5 trunks are occupied. Okay, that's why this is the indirect way of asking what's the remaining probability. Okay, that's why if all 5 trunks are occupied, so that's why we are going to subtract, okay, p of 5, which we already found out to be 0.037, and there is some mistake, I guess, in this part. Okay, please verify for the answer 0.037, and you're subtracting that value from p of 5, which results in, okay, some value. Please verify this. Okay, okay, this value of value for the last question. Okay, so please make a go through this problem and then try to uh, solve it on your own, okay, by using the values, okay, of different questions, sub questions which has been asked. Please verify the uh, answers of this. Okay, next, moving on, the next type of question that might be asked in the examination is uh, to apply the iterative form of first along distribution. Okay, what it says is that a group of how this problem is making utilize of that equation that we have derived, the iterative form of the first along distribution. Okay, in this case, the question in this case is that a group of 20 trunks provides a grade of service of 0.01 when offered 12 alongs of traffic. Okay, what is asking is that how much is the grade of service improved if one extra trunk is added to the group? How much is the grade of service deteriorate, okay, or reduced? The meaning of this word is reduced if one trunk is out of service. See, for example, if you take any system, okay, the service can be improved if you can provide, or you can support more number of calls. Okay, if you have some n number of trunks or outlets available to connect incoming number of calls in a switch, okay, it is always possible to improve the service by adding additional trunks to the outlets. As you can know, it supports more number of calls. That's why he is asking what happens to the grade of service of a system, okay, if a switch has one extra trunk added to the outlet. Okay, similarly, okay, if a grade of service in the second question, sub question is asking what's the grade of service in case a trunk is removed. If a trunk is removed, the possibility with which the service can be provided is very less. The service that can be provided by the system deteriorates or reduces if you keep on removing the outlets which no longer support more number of calls. Okay, this is what is asking. Okay, the detailed explanation of the same problem has been explained in this slide. As you can see, this is the iterative formula that you have seen earlier that we have derived in the first alongs distribution. The same question has been written over here. Okay, the first question is how much is the grade of service improved if one extra trunk is added to the group. Okay, in this case, okay, to solve the first question, we are assuming capital N, the number of trunks to be 21. Why? Because for a present system, you have 20 trunks available. Well, we need to find the grade of service of 21 trunks. That's the question which has been asked. Okay, what's the grade of service improved if one extra trunk? This one extra trunk is 20 plus 1. We are adding one extra trunk to already existing 20 trunks, which results in a 21 number of trunks or outlets in the switch. That's why we are assuming N to be 21. Okay, by the definition of the iterative definition of the first along distribution, Okay, we are going to put the values in the, okay, same definition. Okay, you know, capital A, the traffic offered is, okay, traffic offered is 12 long. You know, E 1 comma n minus 1, the value of n in this case is 20, 21. Okay, subtracting 1 from it results in 20. Okay, so and n is 21 plus 12 times e 1 comma 21 minus 1. Okay, moving on with the equation, we'll get the clear picture of it. The e 1 comma 21 is nothing but 12 times the grade of service of 20 trunks. Okay, this product divided by 21, because 21 is n from the equation, capital N has to be put in the denominator, the first term of the denominator, which is 21 in this case, plus the same product 12 times e power n comma 20. This n comma 20 is 1 comma e power e suffix 1 comma 20. You know, the e suffix 1 comma 20 is nothing nothing but 0.01, which is given in the question. They are providing the grade of service of the system if there are 20 trunks available. You plug in the same value and you'll get a answer like 0.0057. This is the grade of service of the system. This is the grade of service of the system if a system were to have the 21 trunks. Okay, you have the system for the 20 trunks, and he's asking what happens to the grade of service of the system if 21 trunks are available in the same system. So in this case we are using this iterative formula or iterative approach of finding the, okay, the grade of service of 21 trunks in a system. Moving on in the next question, it is asking what's the grade of service of the system if one trunk is being removed. What's the grade of service of the system if one trunk is being removed? Okay, in this case I'm not assuming n is equal to 19. I am assuming n is equal to 20. Why? Because this is the case where we need to find e1 comma 19, e1 comma 19, which is the grade of service of the 19 trunks. Because in a present system you have 20 trunks. If one trunk is being removed from the present system, which results in a 19 trunks. Okay, this is the, you know, the grade of service. This is the the value that you are supposed to find, which is e1 comma 19. Okay, e1 comma 19. So in this second case we are assuming n to be 20. Okay, from the definition of the iterative formula for first echelon distribution, okay, which says e1 comma n is equal to a times e suffix 1 comma n minus 1 over n plus a times e1 comma n minus 1. Okay, I have taken n directly over here, which is 20. Okay, just moving on with the equation, you'll get this equation, okay, which is a times e1 comma 19 n plus a comma 1 comma 19. Here in this case, you know, e1 comma 20, which is 0.01, which is given in the okay question, okay. One way need to find out is the e1 comma 19. Okay, moving on, substitute the value for a, which is given is 12, and the capital N, the number of trunks in this case we are assuming it to be 20. Okay, that's why we are plugging in n is equal to 20, that we have already seen. Okay, and e1 comma 19 is what you need to solve for. Okay, as you can see, if you move on with the equation and you need to solve for the e1 comma 19, the whole simplification is being given over here. Okay, by the, and when you solve for e1 comma 19, which results in 0.017. Okay, look at the grade of service of e1 comma 20 and e1 comma 0.17. Please look at these two. Okay, you have the grade of service in this case, grade of service of, in this case is 0.0057, and the grade of service of e1 comma 19 is 0.017. Among these two, e1 comma 21, that is the grade of service of 21 trunks, is less compared to the grade of service of 19 trunks. Okay, that's why the value of the grade of service should always be lesser. More the grade of service value, okay, lesser the quality of service provided by the system. Okay, as you can see, it is very clear that when you remove a trunk from a system, the grade of service deteriorates. The grade of service deteriorates. Okay, so this is about the first along distribution. Okay, so as I have 5 more minutes left. Okay, I am going to create one more session and we'll be meeting at 11:45.